All right, so chapter 10 is the t-test for two independent samples. So when we think about the independent measures design, we have to realize that most research studies are going to be comparing two or more sets of data because we've got the data from two completely different independent participation groups. We've got the independent measures research design or the between subjects design. Data from the same or related subject groups, such as a within subjects design or repeated measures research design, can also be used. The way we compute procedures for each design are different. Each design has its own strengths and weaknesses, and only the between subjects design are considered in this chapter. In the next chapter, chapter 11, that's when we'll talk about the repeated measures research design. So here's an example in figure 10.1 of the structure of an independent measures research design. You can see we've got sample A and we've got sample B, and then we calculate those totals for each group. In 10-2, we discuss the hypothesis and independent measures T statistics. So when we have the null hypothesis for the independent measures test, it means that there's no difference between the population means. And when we have the alternative hypothesis for the independent measures test, it means there is a mean difference between the two scores. Here's the basic structure of the T statistic and the formula we'll use to calculate that. The estimated standard error is a measure of the standard or average distance between the sample statistic and the population parameter. How much difference there is reasonable to expect between two sample means if the null hypothesis is true. We also have to consider the variability of the differences between the scores. Why would we add the sample measurement errors but subtract sample means to calculate a different score? Because the variability for the difference in scores is found by adding the variability for each of the two populations. So here's a sample from 10.2 of two population distributions, and you can see their differences, 20 points and 50 points. Pooled variance is an equation that shows the standard error concept, but is unbiased only if the two samples are exactly the same size. And pooled variance provides an unbiased basis for calculating that standard error. So we can see here the estimated standard error can then also be calculated using the pooled variance estimate. And there's that formula. And then the final formula in degrees of freedom is the independent measures T statistic, which is the sample mean difference minus the population mean difference divided by the estimated standard error. And we've got degrees of freedom for the T statistic is measured as DF for the first sample and DF and DF for the second sample. So let's go ahead and do a learning check. Which combination of factors is most likely to produce a significant value for an independent measures T statistic? Go ahead and think for a moment about that. And the correct answer is going to be D, a large mean difference and a small sample variance. Here's another learning check in true false. If both samples have a sample size of 10, the independent measures T statistic will have a degrees of freedom that equal 19. And then for the independent measures T statistic, the estimated standard error measures how much difference is reasonable to expect between the sample means if there is no treatment effect. Go ahead and take a few moments to think about both of those. And the correct answer is false and true. And you can see for the first one, that was calculated to 18. And then that is a true interpretation here. So instead of it being 19, it's actually 18. The independent measures hypothesis test uses the same 4 steps as the other hypothesis tests we discussed in previous chapters. You're going to state the hypothesis and select that alpha level, usually 0.05. You're going to locate the critical region, obtain the data, and compute the test statistic, and then you're going to make a decision. Here's an example in figure 10.3 of the critical region that exists. You have directional hypotheses and one-tailed tests, and those directional tests are only used when predicting a specific direction of the difference, if it's being justified, when you can locate the critical region in the appropriate tail, and when you can report the use of a one-tailed test explicitly in the research report. There are also some assumptions that underlie independent measures with using a T formula. That's when we have observations within each sample which must be independent. We have the 2 populations from which the samples are selected, which must be normal. And we have the 2 populations from which the samples are selected, which must have equal variances. And that is usually called the homogeneity of variance. So here's how we test for the homogeneity of variance. We use F max test, which is a large value that indicates a large difference between the sample variances. When you have a small value that's near 1, it indicates a similar sample variance, and that homogeneity assumption is reasonable. We also have the pooled variance of a alternative, and this exists if a sample information suggests a violation of homogeneity of variance. So we'd have to calculate that standard error and then adjust for the degrees of freedom for the t-test. We also have to consider the effect size and confidence intervals for those independent measures. If we reject the null hypothesis, then that effect size should be determined by either using Cohen's estimated D or the percentage of variance if it's explained. You can see those different formulas there. We also have to consider confidence intervals. That's when we have the sample mean difference, and it's used to estimate the population mean difference. So we use a T equation, and it's solved for the unknown, and then solved for the unknown parameter. We also have some confidence intervals in the hypothesis tests. This is when we have an estimation which can provide an indication of the size of the treatment effect. This estimation can provide an indication of the significance of the effect. And if the interval contains 0, then it is not a significant effect. If the interval does not contain 0, then that tells us that the treatment effect was significant. So here's an example from figure 10.4 with a 95% confidence interval for the population mean difference from example 10.6. So when we get ready to report the results of the independent measures t-test, we have to report whether the difference between the 2 groups was significant. We have to be able to report descriptive statistics for each of those groups. We have to report the t statistic and the degrees of freedom. We have to report that p-value, and we have to be able to report the confidence interval immediately after t. The standard error is directly related to that sample variance because a larger variance leads to a larger error It also leads to a smaller value of t, which is usually closer to 0. And that's going to reduce the likelihood of finding a significant result. Because larger samples produce smaller errors, larger samples then lead to a larger value for the t statistic. So here's an example of that in 10.5 with two sample distributions that represent two different treatment methods. Let's go ahead and do an additional learning check. For an independent measures research study, the value of Cohen's d and r squared helps to describe what? Give you a few moments to think about the correct answer. And you should have gotten C, how much difference there is between those two treatments. Let's also try some true false. The homogeneity assumption requires the two sample variances to be equal. If the researcher reports that T6 equals 1.98 and P is greater than 0.05, then the null hypothesis will be rejected. Give you a few moments to think about those answers. And they are false and false. The assumption requires equal population variances, but the test is valid if sample variances are similar, and we reject the null hypothesis when our p-value is greater than 0.05 and t is less than the critical value of t. So you guys can also see how SPSS, the statistical program, can have the output for the example in 10.2. So hopefully all of these numbers make sense. And hopefully this explanation gives you some additional ideas of how to measure those independent, how to make those independent measures for a t-test.